Afternoon, everyone. Welcome to the High Performance Computing Showcase, Faculty Showcase at Cal State San Bernardino. My name is Sam Sudhakar. I serve as the Vice President and CIO at CSUSB. And it's a pleasure to have you all, especially our faculty members, joining us this afternoon to showcase their good work using the High Performance Computing program at Cal State San Bernardino. This high-performance computing program at CSUSB is a collaborative effort between Information Technology Services and our faculty community in collaboration with UC San Diego and the San Diego Supercomputing Center. We appreciate our colleagues from UCSD and the SDC for joining us this afternoon, and to our colleagues at CENIC who provided us the infrastructure that allows us to access high-performance computing resources from across the country. This program is really driven by our faculty community, who are high-end researchers who use the high-performance computing resources to advance their research and their teaching to our students. We appreciate our faculty community and also want to acknowledge our ITS folks, ITS professionals, who have provided us the infrastructure for our faculty to use in the high-performance computing program, especially Gerard, James, and Dong Wu, who have already joined us, and for Dr. Brad Owen and Dr. Young Soo for providing leadership to our faculty community in the use of this resource. You are here for a treat from our faculty community as they showcase how they're using the program to advance their research and their teaching to our students, and how our students are also benefiting by the HPC program at CSUSB. So I'll turn it over to our Associate Vice Provost for Faculty Affairs and Development, Dr. Kevin Grisham, who will provide welcoming remarks as well. Dr. Grisham.
Thank you, VP Sudhakar. So welcome, good morning. Thank you for joining us. On behalf of the Provost Rafiq Mohammed and our entire team in the Division of Academic Affairs, welcome to this amazing presentation. I look forward to seeing the presentations today. And I just want to say thank you to all of our faculty, for the work that they're doing to in this program as well as other programs, really to connect really the research piece that they're doing with our students. And I can't say enough about the amazing faculty we have here at CSUSB. I've been honored to serve alongside them for 15 years, and now in this role I get to work with them in a different capacity. But I can tell you that we have some of the best faculty in the entire nation. And I think the CSUSB high performance computing allows us to sort of elevate that and show that not only in R2, but we're a nationally public university. We have been doing this kind of work for many years. And so thank you once again to all the faculty for all the work you put in. I know it's a lot on top of everything else you do to serve our students. And thank you for connecting what you do with our students, because as we often say, our North Star at this campus is our students, and we do everything for our students. And I think all the things we'll see today sort of show how that happens, because you're able to take your research and tie in students or use that research in the classroom. So thank you once again. And thank you to the entire team that's worked on this, both faculty and staff, and to Dr. Sudhakar as well as Dr. Owen as well. So thank you.
Thank you, Dr. Grisham. Thank you, Dr. Sudhakar. Before I introduce our terrific faculty presenters, I would like to again recognize our high performance computing faculty fellow, Dr. Young Soo Kim, who's here with us, and also our high performance computing consultants, Dr. Dong Wu and Mr. James McDonald. I think, Dong Wu is with us today. Young Soo works with faculty to understand their project needs, while Dong Wu and James provide technical consultation and support to implement what is needed for faculty projects. Also, I would like to share proudly with you all that Information Technology Services was awarded $1.2 million of a $6.7 million NSF grant in partnership with UCSD and San Diego State University. The grant is called Cyber Training and Developing a Research Computing and Data Professionals Community. And our part of the grant supports the development of personnel and resources to advance faculty's use of high-performance computing at CSUSB. The grant has a focus on developing these unique skill sets at Hispanic serving institutions. And the grant will greatly improve our ability to support our faculty and will be a key recruitment resource as we continue to expand on graduate student and faculty recruitment efforts. So I just want to note that all of our faculty are welcome to participate in this program. And if any of our audience joining today would like to learn more about high performance computing here at CSUSB, please email Young Sue at the email address I'm going to put in chat right now. Let's see. Okay, let's see. We need to go. Okay, I'll make sure that goes to our audience here in a moment. With that, let's go on to the exciting work done by our high performance computing faculty. Our first presenter is Dr. Benjamin Becerra, Assistant Professor in the Department of Information Decision Sciences. His presentation is entitled Predicting Pediatric Sleep Apnea Using Machine Learning. Dr. Becerra, please.
Thank you. Yeah, if you don't mind, could you enable the screen share real quick?
Yes, you're able to share your screen.
Not yet. Well, while that's coming in, thank you very much for the introduction. I really appreciate it. So there it goes. And I just want to say that this project has been ongoing for a couple of years. And I really like how using the resources that we have on campus that so many students can be a part of it. So even though I'm going to show you like a project, this is not done by me. This is done by an entire team of students that have come together along with myself to kind of put this together. So with that, I'd like to start. This is going to be a presentation on my the project that I'm leading, predicting pediatric sleep apnea using machine learning. Okay, so just to give a little bit of a general background, sleep apnea is quite a large issue in the United States. For example, it's estimated that around 22 million people suffer from this condition. And of adults, it's believed that up to 26% have sleep apnea. Well, that's already quite a large number. Just to add to that, it's thought that up to 80% of people with obstructive sleep apnea or OSA are still not diagnosed. And of those undiagnosed people, it's thought that 1 to 5% of children are those who are going to be having OSA. So why is this an issue? So particularly focusing among children, so that pediatric population, if you have OSA at such a young age, it can lead to long-term morbidity, meaning that over time, it can result in numerous diseases and issues with the body that are really compounding over time. Furthermore, you might see some other issues such as coexisting conditions such as asthma might actually be worsened. Oh, I don't have my pointer on. So for example, asthma and other co-occurring conditions along with OSA can start to increase or worsen some of the symptoms that can occur. School performance, something else that can be affected as well by not being able to sleep. And furthermore, mental illnesses are also at increased risk for children who have obstructive sleep apnea and are not their condition is not found in time. But if it's found in time, interestingly, it's actually curable. Most of the time using tonsillectomy and adenoidectomy. So that's removal of the tonsils and the adenoids. So while it's quite an issue, there does seem to be some light at the end of the tunnel. So because of that fact that it is possible to cure this condition at a young age if caught in time, the background behind the study is that, well, if there's a tool that can be used to predict whether or not a child might have sleep apnea, particularly in a clinical setting, then that might be a very promising screening tool that can prevent a lot of these issues that I just mentioned. And machine learning is actually a way that might be a good method to try, considering how it can use a variety of data sources in order to predict outcomes such as sleep apnea. So for this project, we're using a variety of data sets that all come from the Agency for Healthcare Research and Quality's Healthcare Cost and Utilization Project. Specifically, there's 4 sets of databases within the HCUP, or the Healthcare Cost and Utilization Project. And that focuses on inpatient data, so staying in the hospital, emergency department data, ambulatory surgery, so going into the hospital and then leaving the same day, as well as a readmissions database that tracks if people go to the hospital and then come back subsequently. So these are the data sets that we're using. And I'll talk a little bit about the first one, the NIS, or the National Inpatient Sample. So these data sets are available through AHRQ, as I just mentioned, and they are quite large in terms of the size of the data sets. So each year, because this is a nationally representative data set from encounters around the country, for just looking at the smallest data set, which is NIS, that's already going to be 7 million records per year. And we're talking probably about 5 years of data right now. So you can imagine how much data there's going to be. And not only adding to the number of observations, so thinking about going up and down the table, we can also go left and right on that table. And sure enough, this is electronic health records. So every single possible diagnosis can be, or procedure can be coded out of this data set. So there's a lot of data. So what do we do? Well, first of all, for this model, or for what we're starting with, we are using just a single year of data in order to get the methods down right. And as this is the largest publicly available inpatient database in the United States, it does have a variety of variables or features that can help us to answer our research question. But along with that comes this thing known as like the curse of dimensionality. You have too much stuff to look at. So it would be practically impossible to be doing this locally on our computers without looking at really, really tiny, like micro data sets of this thing. In a previous presentation, you might have heard me mention that we used Google Colab, and that thing kept crashing on us because it just does not provide the available resources that we need. So luckily, we have the National Research Platform, or NRP, and we're using JupyterLab. And again, thank you so much for this project, for this program or platform that has allowed us to do so. Because we have a lot of data, and it's really difficult to crunch that data, so to speak, on your local computer, especially for student research when a lot of them are using laptops. So my 64 gig workstation, it can handle it more or less, but I can't expect that of other researchers in my group. So this really has allowed more collaborative research, especially among students. Now I'm going to skip to where we're currently at, because I think I can have like an hour presentation on just like the lessons learned about some of the things that we had in our research. But where we're at now is we're actually looking to try to use a program, or like a platform rather, called Apache Spark. And basically that's going to allow us to load the large data sets and analyze them kind of within the same environment. And we're continue to work on that. Right now, I have a graduate student, and 2 of my other students are graduating from this project and from their degree. So I'm looking to start recruiting additional students for this project. And then we'll continue on with this pipeline, where we're going to try to create models that are based off a GPU framework. So not only does this platform support analyzing large data sets due to the scalability, so we have that ability to change the resources that we need. GPUs are really, really expensive. So this is another thing that wouldn't have been possible without this program, or even consider it for my research, because I don't have an external grant. So great for students and great for myself. And the goal then is to proceed with machine learning that is a bit more interpretable. So that's kind of the goal with this, since our research is along the lines of health equity. And just before my time runs out, I do want to mention that I believe that the NRP has been very invaluable to my courses, especially these two that I teach. So one is big data analytics, and another is advanced application development. In the first class, big data analytics, take a guess, we're analyzing big data. So it's really helpful that I'm actually able to give them large data and they can analyze it. So for example, in like 2 more weeks, we're going to have a module on Spark, what I just mentioned, which is possible to do locally, but you're probably going to give them like a tinier data set because it's probably going to crash their computer, basically. So really grateful for that, to be able to have that, especially because we are using big data in this course. And also it's super convenient for advanced application development, because this is a cloud-based platform where students can basically log in anywhere. I've seen them log in on their tablets and do coding work for this class. So that's super helpful. And not only that, but like the HPCP team has been super helpful. For example, I mentioned, hey, I noticed students are using this VS Code thing. Is there any way we can get that on the platform? And sure enough, everyone has started to work to get that to happen. So I'm very grateful for that. And so I see some students starting to use that one too. Okay. So again, acknowledgements to the high performance computing program team, as well as the OSR that has funded my students to continue to do research, my external collaborator, and other funding sources as part of this project. So thank you very much. And I know we have questions at the end, so we'll wait for that.
Thank you, Dr. Becerra. It's so exciting to see the ongoing progress of this project. Thank you. Our next presenters are Dr. Kate Liska, who is the CSUSB Benson and Pamela Hare Fellow in Egyptology, and Professor Brian Kramer, who is research Egyptologist and educator at the CSUSB Robert and Frances Fullerton Museum of Art. They will present on high performance computing to make virtual 3D models of ancient Egyptian archaeology. Dr. Liska and Professor Kramer, please.
Thank you so much for having us here today. We are really thrilled to be a member of the group today, to be able to share what we're doing. I want to thank ATI, Brad Owen, Sam Sudhakar, Dung Vu, and all the others who have invited us here to speak. Archaeology, and our subset of archaeology, namely Egyptology, is not traditionally concerned with computationally intensive computing resources. But as we hope to show you, there are new technologies that have revolutionized our field, but also require various types of high performance computing. Now, our high performance computing projects usually come from our archaeological data that we gather in Egypt at the site of Wadi El Hudi. And we've been working at Wadi El Hudi for the better part of 8 years now. So if you want to know more about our archaeological excavations, please check out our website, wadielhudi.com, for more information. But basically at Wadi El Hudi, we investigate a very large mining region in Egypt's eastern desert that has numerous mines, buildings, evidence for the people who worked in those mines. And the ancient Egyptians and others who went to Wadi El Hudi were basically looking for various minerals there that include things like amethyst, copper, amazonite, garnet, gold, and others. And these the archaeological sites that they created were occupied from the lower Paleolithic period, about 1 million years ago, until the Middle Ages, so about 700 years ago. But we're particularly interested in sites that date to Egypt's Middle Kingdom, so that's about 2000 to about 1700 BCE. And these mining camps, hieroglyphic inscriptions, and other archaeological remains from this period are so remarkably well preserved that they're basically in the state that they were in 4,000 years ago when they were abandoned. And as we hope to show you today, the future of archaeology has a great deal of overlap with technologies used in graphic design, computer imaging, and even video game development. In the last 10 to 15 years, archaeology has started using tools for high resolution, dense recording of imagery of objects in the real world. And this development parallels similar revolutions using high-res imagery in material science, engineering, design, art, and more. Now, in the case of archaeology, we are most concerned about high resolution of visualization of two major things, either individual artifacts or archaeological contexts. And eventually we'd like to put the 3D artifacts back into the archaeological context too, in virtual situations. Now, artifacts are individual objects that relate to human activities of the past, and archaeologists heuristically investigate artifacts through examining their material properties by looking at archaeological contexts that they're found in. And here you can see a Middle Stone Age Paleolithic tool found at Site 2 on the left, and on the right there's an inscribed hieroglyphic stele from Site 4. Archaeological contexts are spatially discrete parts of the real world with evidence of activities of humans performed there in the past. Now, conventionally, contexts include things like entire archaeological sites, as well as the smaller excavation units in them. Archaeological sites are broadly defined as areas on the landscape that human activities took place, whereas the excavation units are much smaller and more discrete, basically the area that we decided to excavate to examine human activities. So on the left, you have the entire archaeological site of Site 11 at Wadi El Hudi, whereas on the right, you have a single excavation unit that we excavated in January this year from Site 21. And archaeologists are very interested with visualizing the real world so that we can understand it, so that we can study it. And 3D technology helps us do a better job because we can do it at home and we can share it with others. Now, traditionally, for the last 100 years or more, this was done by making maps and by doing technical drawings, and we still do that when they are suitable, especially for conventional representations in things like pottery and excavation units. So on the left, you see a standard ceramic bowl, and on the right, there's an excavation drawing. But in the last 10 to 15 years, using only cameras, the technology of digital photogrammetry has really come into its own affordable and portable technology for anyone to be able to make highly detailed digital renders of actual archaeological artifacts and contexts.
So 3D modeling and photogrammetry takes advantage of the optics and other geometric characteristics intrinsic to cameras to spatially map stationary objects. This technology essentially uses a series of photographs to map out things that are commonly identifiable in them with a computer vision algorithm called structure from motion, or SFM. Although this kind of processing is essentially something that people have been doing in an analog way for more than half a century, especially to make things like topographical maps from aerial photos, it is the power of computers to mine digital photographs for visual data and to process repetitive photogrammetric equations that has opened up the whole field of 3D rendering with photogrammetry. Several computer programs have been developed for this work, many implementing similar structure from motion processing algorithms. We happen to use Agisoft Metashape, which is what a lot of archaeologists use nowadays. These programs can derive dense point clouds representing commonly visible spots on some or all of the photographs you feed it. These dense clouds are sometimes as good or better than the data that you could get from LiDAR scanning the object or the context, depending on what kind of photographs you're actually making. But it's more importantly, it's something that you can do with any camera. And so it's highly portable, it's versatile, and it's scalable in terms of workflow. This happens to be a video of the process as we have been using it at RAFMA in the museum on CSUSB campus to scan objects from Egypt in 3D and put them on display as part of the exhibit there. As we are doing there, the process of 3D scanning objects consists of taking a series of about 60 photographs for each side of an object, and then feeding them into the program. The program runs the 3D model for each side, and then we bring the two sides together, hopefully seamlessly, to make one solid model of the entire object. So in addition to making our data much more high res, this type of technology also addresses a serious problem that we have and other archaeologists have who work in similar situations around the world. Unfortunately, the threats to the preservation of the archaeological record that we have to deal with mean that much of our work has to be considered rescue documentation. And for rescue documentation, speed is paramount. The area of the desert that we are working in is currently being developed for gold mining. Every time we come back to the field, there is a new gold mine that has set a claim on part of the desert. And when we discover an archaeological site around gold mines, we never know if we will be able to go back more than the few hours that we put into them in one season. Sometimes it turns out like this archaeological site that an entire set of illegal miners show up and destroy the site. The photogrammetric technology that we're using for mapping and documenting is hugely helpful for the challenges that we are facing in this situation. And perhaps the best means of illustrating this point is to show you a particular case. This is our archaeological site, number 51. We first discovered this site just in January when two of our team working in the desert wandered off from the other archaeological site we were looking at on the day. It is a rock art site and a settlement site consisting of a series of caves made in overhangs of sandstone. The walls on these caves are covered with about 50 or more petroglyphs showing animals, hunters, herdsmen, and tallies, and there's at least one hieroglyphic inscription. As soon as we found out about Site 51, we realized we had to make time to come and document this site. But in the end, we could only give it one more day of our season. So how do you approach making a map of a site that is as complex as this one in just one day? Well, in the 7 hours of that one day we happen to have, we took a set of about 3,000 photographs from as many practical angles as possible, crawling over these rocks. And using these, we were able to create a 3D model of Site 51. And it's actually a fairly good model. I'm very happy with it. I was particularly happy that we were able to capture the cave system that exists under the rock overhangs. That's not always something that successfully turns out, but in this case it did. And importantly, each photograph that we took of the inscriptions on these rocks is incorporated in the 3D model, and therefore we can derive the location of those inscriptions and their spatial coordinates from the 3D model. This 3D model therefore serves as a 3D map that allows us to document the site in the traditional way. And we only had 7 hours to do it in. So as you can see, this type of technology allows us to move at a speed and to deal with problems of documentation with a much freer hand than if we had using the traditional methods such as surveying with total stations or even just using GPS devices. So that's why we use the technology we do for the speed and the high resolution data. But the question we're answering today is, how did the high performance computing resources become a necessary part of the process? And the answer to this question is that the scale of the data can sometimes outstrip our ability to process it. When we deal with an archaeological site that is highly complex and has a lot of preserved remains that we want to capture, then the number of photographs that we have to handle will start to pile up. And the best example of this is what I'm showing you here. It is an archaeological site that we visited for only 2 days in January. This is the fortified mining settlement at Dihmet South. As you can see, it is a walled structure consisting of at least 3 large areas of complicated walls and rooms. Each room probably had a special function, and the architectural arrangement of other features around them, such as turrets in the walls, probably had implications for the use of space in the fort. So we're very interested in high resolution detail of the architecture. Well, we also happen to be the first archaeological mission to ever visit here, and we only had those 2 days, and we may not get a chance to go back ever again. So how do we deal with this? Well, we did it like we did at Site 51. We took as many photos as we possibly could. And in doing so, we took about 12,000 photos of the architecture around Dihmet South in about the 2-day time that we had. So in order to make a 3D model, there's a problem in dealing with 12,000 photographs. How do we process them? For every photograph that we use in Metashape, Metashape will sample the photograph down to the pixel level for the data used in the photogrammetric equations, and it will hold that data in the computer's RAM while it processes those equations. With 12,000 photographs, it's just not going to work properly on most of the machines that we have available. And this happens to be the real ceiling for this kind of work using photogrammetry in modeling archaeological sites, is that eventually you may reach the capacity of the RAM for your computer, and the quality of your GPU also matters significantly in the processing speed. And this is where the high-intensity computing resources came to bear. For the last 4 years, ATI, and especially Dong Vu, thank you, Dong, has facilitated our work in these complicated modeling tasks by implementing a workstation on the Pacific Research Cluster with a customized RAM capacity and GPU resources. And in the latest build that I've been using to process these 12,000 photographs from DIFMIT South, which you see here, we've been using 4 A100 GPUs for processing, and had a capacity of 512 gigabytes of RAM, which is far outstrip most builds on computers you can put on a desktop nowadays. For the most part, the data-intensive part of this site, for the most data-intensive part of this site, these resources shorten the processing time down significantly. In this case, it's about less than 12 hours per section of the archaeological site. On traditional computers, sometimes that could take days to process, even on very high process and RAM enabled computers. So unfortunately, the results of processing DIFMIT South still need to be cleaned and edited, so I can't show you that archaeological site, but it's pretty indicative of the kind of effort and time it takes to build any of the larger archaeological sites that we have at Wadi al-Hudi, such as at Site 9. It's actually fairly similar in size. As you can see from this render of the archaeological site in Unreal Engine, we have used most of our 3D scans, bringing them together into archaeological contexts in a kind of a digital version of Wadi al-Hudi. We're doing this in Unreal Engine 5. When it's finished, this version, this virtual version of the region will allow us to visualize the entirety of Wadi al-Hudi landscape in one walkthrough experience. Wadi al-Hudi is not a place that other archaeologists or tourists can go. We have to actually get a very special and kind of difficult to obtain set of permissions to do our work there every year. But it is our hope that one day we can bring people there virtually to allow them to see the archaeological sites and the other excavation contexts that we've created, and even see things that will not be there now, the digital 3D models of artifacts that we have removed and taken to a safe storage location in Egypt for the archaeological service to handle. So hopefully then people will get a sense of how this archaeological region worked as a whole in this virtual version we're building. So thank you for helping us with this, ATI, Dong Vu, and everybody else, and for providing this amazing resources of the PRP. Just the numbers show that we couldn't have done it without you. So thanks a lot.
Thank you.
Thank you, Professor Kramer. Thank you, Dr. Liska. Amazing, very exciting work you're doing there. Again, a project which is ongoing and a multi-year project with high performance computing. Thank you. Our next presenter is Dr. Kimberly Cousins, professor and since 2017, chair of the Department of Chemistry and Biochemistry. Dr. Cousins' presentation is entitled Materials Genome Approach to Functional Materials Discovery, First Principles Calculations. Dr. Cousins, please.
Thank you, Brad. Before I start sharing my slides, you can hear me, right? Yeah. Before I start sharing my slides, I noticed I had a tab open on my browser that may look familiar to some of you who've used Jupyter Notebook. This is a calculation running right now with a brand new warning on it. But I wanted to point out that the team, the wonderful team with Dong Vu and Young-sun Kim, have set up this individualized little server for me with different student folders and a shared location, and it's really, really helpful. So stop the share. Start with my slides. So although my name is on the presentation, most of the work that has been done by my students over the years. Oops. Move to the next one. There we go. So the Materials Genome Initiative is about a decade old, and it was slated to use rational approaches to design of new materials, everything from electronics to other things that where the materials themselves have a property that you can use. Our approach to functional materials started with something called ferroelectrics, which are a subset of something called pyroelectrics, which are a subset of something called piezoelectrics. So in ferroelectrics, you have a material that's polar, and I have it drawn as a little cube here, but in fact, materials that are crystalline have repeating cubic-like or modified structures. And in ferroelectrics, you can actually change the polarity of the material by applying an electric field. So this ends up being important for a lot of microelectronics. There we go. Slides are doing weird things. There we go. So another material that has a huge range of applications is piezoelectrics, and they are polar materials, things that have a polarity that can be changed in shape or size by the application of an electric field. Or conversely, if you squish or extend the material, it generates an electric field. And in case that seems pretty scientific to you, I was going to tell you a little bit about some applications. Most of us are familiar with piezoelectric spark generators on a barbecue grill or a gas stove, where you turn on the dial and it goes click, 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 click. We're providing pressure on a surface that's generating energy in the form of a spark. So that's a very low-tech application of piezoelectrics. Piezoelectrics are also involved in all kinds of things from sonar to ultrasound sensors. And one of the really cool applications could be in the future, changing the shape of a piezoelectric by being a wearable electronic, like this one right here. And then that would power an internal machine, such as a pacemaker. So we also use piezoelectrics in our scientific instruments to do very, very small changes in size and shape, for example, to see the shape of a surface of atoms. And ferroelectrics, the first class I talked about, are used for solid state memory. They have the two different polarity states, which are like the ones and the zeros on a computer. And then there's one related property we've worked with by discovery, and that is nonlinear optics. Those are materials where you shine one wavelength of light and the material itself varies the wavelength of light. It's the basis of how lasers are made. Okay, so in order to have these properties, crystallographic materials have to have certain properties, including the polarity, which means that it's part of a non-centrosymmetric space group. That's something we can look in databases for. And something called pseudosymmetry, if it's going to be ferroelectric. It has to be able to change from one polar state to another. And if it's electricity, polarity changes with pressure, and crystal structures that vary with internal energies, including pyroelectrics, are basically energy changes the crystal size and shape. And if there's unpaired electrons in the system, that becomes even more functional, a type of thing called ferromagnetic. Now, in terms of high energy calculations, we can actually calculate elasticity, polarity, changes with pressure. We can look at the reversal of polarity through being a potential ferroelectric. We can look at changes in crystal structure with changes in energy. We can look at unpaired electrons. So all of those things are subject to calculation. And we do these calculations prior to moving materials forward to our experimental collaborators, because the calculations, although they take time, are faster than spending a year making a material and testing it. So just as an example of this, our research is kind of unique in that we're working with organic and organometallic ferro and other functional materials. Most of the ones that are on the market now that do piezoelectricity and ferroelectric behavior are inorganic, and many of them contain lead, which is not an environmentally good thing. Others of them are very, very brittle because they're ceramics. And so using organic materials could potentially improve those outcomes. A known ferroelectric that was reported first in 2013 is diisopropyl ammonium bromide. And a lot of our early calculations had to do with defining exactly how the polarity change took place. You actually have a polar material one way that goes through a nonpolar sort of random intermediate to form the polarity the other way. So we did some what's called molecular dynamics calculations to watch this conversion from one form to another. We then went to look for other examples, things that people don't know yet. They know the structures, but they don't know the properties. And we used the Cambridge Crystallographic Database for that. And then once we've discovered potential candidates, we use our plane wave density functional calculations, which is exactly what I showed on the very first screen running on my Jupyter notebook. Okay. So one of our successes along this route is something we call MEL. It has a polar form that can convert with very low energy barrier to another polar form. We discovered this material a few years ago. Luke Vincent, a student, was the one who found it, did some calculations. We passed it on to our experimental collaborators who were able to grow it and do some measurements on it, including seeing a phase change at 124 degrees, which is an indicator of ferroelectric behavior. And although we don't yet have any ferroelectric measurements for it, we did find that it's a very good nonlinear optic. Now, what you're seeing here is the very bright white laser light going through the material, but when you put a filter over it, you can see the green light that's being produced. And this was actually from a student-grown crystal based on this material. I neglected to start my clock. How am I doing for time? Okay. Another example that's a more recent student, Sarah Rodriguez, who's actually just earned a master's, was working on, was a donor acceptor compound. Again, we found in a database, we did first principles calculations, we actually grew some crystals, and we're waiting for some experimental results. One of the interesting things is that another group used a completely different methodology to do calculations as a predicted ferroelectric and came up with a very, very small ferroelectric coefficient. We had a screening algorithm that gave us a ferroelectric coefficient that is commercially viable. And then we did our first principles calculation and got an even higher number. So we're really excited about this material. We did get some piezoelectric force microscopy results, which were preliminary and did tell us that it has that potential to have those piezoelectric and ferroelectric properties. We've also looked for multiferroics, which is things that have both electric and magnetic properties. And one summer, Carolina, who's just now entering graduate school, came up with some a whole set of interesting materials that, again, have a very low barrier for conversion from one form to another and have different polarities, and we believe would be very powerful piezo and ferroelectrics, very small effects, but very low energy for conversion. And they're made out of organic materials and metals. So I'll bring that to what we're actually doing now with the resources provided by this project. Up until now, all of our computations have been done using accounts from the NSF Exceed project. But that, among other things, involves regular proposals and everything, and they're not always set up to provide the kind of support that we're getting locally. And I've been really happy with getting started with our projects here. The two projects that we're working on right now, one of them is a Catane-based metal organic framework. That's the hairy thing on the left. And one of them is a biocompatible co-crystals. We found a bunch of co-crystals that are made out of things that have already been FDA approved as nutraceuticals, pharmaceuticals, and could potentially be piezoelectric materials as well. So here's where the problem becomes. This is the unit cell for the large hairy thing you saw on the other page. It actually has over 1,000 atoms in it, all of which have many electrons, except hydrogen, which only has one. But cobalt has a ton of electrons. And so it's a really big calculation because our calculations calculate the electron density interacting with each electrons, and it goes through many iterative cycles. So it is quite the biggest thing we've ever tried to calculate. We picked this system because it is known to be compressible, which is one of the features we needed for our potential piezoelectric properties. And now that we're actually getting some calculations to run, we're really excited to see what kind of piezoelectric coefficients are predicted. Oh, it started over again. And of course, I once again want to thank the local support. This has been the best support I've gotten for computing, and I've been doing computing research since I got here in 1991 on increasingly more complex platforms, but this support has been really good from this project. I've also listed the other projects that have supported our time and our computer time, and thank you.
Thank you, Dr. Cousins. What exciting work. To my lay eyes, it looks like it's so important, the application, eventual application of what you're doing. Amazing. Thank you. Our last presentation, our last presenters are Dr. Nazreen Mohabati and Dr. Sepida Alavi, who are both assistant professors of logistics and supply chain management in the Department of Information and Decision Sciences. Their presentation is entitled Optimizing Traffic Monitoring Using Drones. Dr. Mohabati and Dr. Alavi, please.
Thank you so much, Brad, for inviting us and for the opportunity to share our research in the HPCP Faculty Showcase. Dr. Mohabati and I are conducting a research on optimizing traffic monitoring using drones, and we would like to share our research throughout this presentation. Well, first of all, we will have an introduction, then we will go over the problem definition. We will talk about the methodology and our mathematical model, and we will talk about how we run our experiments using the high-performance computing resources, and finally, we conclude. Well, the usage of unmanned aerial vehicles known as drones have increased rapidly over the past years because of their mobility, flexibility, and environmental contributions. And also, the advances in artificial intelligence and machine learning techniques have promoted the performance of drones, which makes them applicable in several areas. So the drones have a wide range of applications. For example, they are used in delivering the goods and products to the customers, or delivering the medical supplies to the patients who are in urgent need of receiving those drugs. They can be used for data collection. There are drones that have some cameras embedded on them. So they are used for capturing images in photography, mapping, and surveying. And of course, they have a wide range of applications in monitoring. They are used in surveillance and inspection for military purposes. Also, they are used in agricultural areas for crop and soil monitoring. They can be used in environmental areas for air quality monitoring, and also for monitoring traffic on highways and being able to respond to emergency situations. And this is the focus of our research. Well, there are traditional methods for monitoring highway traffic networks, such as helicopters, police patrols, sensors, and cameras, but all these methods have some disadvantages. For example, the police patrol itself can add to the congestion in the traffic networks. So instead, drones are better solutions and can address these challenges in logistics. Well, they can communicate communicate and transfer the data on traffic in the real time. So it provides the traffic managers with the chance of identifying and responding to traffic bottlenecks, and they can take appropriate actions to hopefully reduce the traffic congestions and improve traffic flows. Well, drones have these significant contributions because of their several advantages and characteristics. They have high mobility and flexibility. They fly over the traffic, so they don't add to the congestion, and they can monitor different traffic hotspots and areas with changing traffic patterns. They are more cost-effective solutions compared to the traditional methods, and they can cover a wider range within less amount of time. So this reduces the need for installing several different sensors and cameras on different parts of the highway. And of course, because of their environmental benefits, they are considered as sustainable solutions when it comes to monitoring the traffic networks. Well, the drones are really efficient and effective in capturing emergency situations. For example, if a severe accident has happened on the highway, it can be communicated in the real time, and they can send quickly all the supporting aid to that location where there are injured people throughout that accident. So we have looked into the papers in the literature for traffic monitoring, and there is not any paper that looks into modeling and using drones for traffic monitoring, specifically providing a model for routing and scheduling drones. And they are not looking at optimizing the operations of multiple drones, not only one drone simultaneously in the highway network. So especially on the locations of highway where there's high likelihood of accidents happening, there's a need to have multiple visits throughout the day to provide fast emergency responses. All the papers in the literature have looked at having only one visit to every location on the highway, but this is not realistic, as there needs to be multiple repeated visits to all the locations that have high congestions and have high probability of accidents to be able to manage the fast responses better. So therefore, there are these gaps in the literature, and it has motivated the contribution of our study. So we have introduced a novel mathematical model to tackle the challenging task of routing and scheduling multiple drones in a highway network for the purpose of traffic monitoring and providing fast emergency responses. Now I would like to turn it over to my colleague, Dr. Mohabbati, to continue.
Thank you, Dr. Alavi. Good afternoon, everyone. I would like to talk briefly about the methodology of our research. This is an ongoing research, so we're still working on that, but I don't want to bore you with the details of modeling, just general information. So in a mathematical model, always we have some input data, and then we run the model to find some outputs. Here, sets and parameters are considered as our input to the model, and then at the end, we expect model to give us the optimum values for decision variables. For example, in our model, we assume that we have m number of drones that gonna visit n number of locations, and each location going to be visited multiple times during 24 hours. At the end, after running the model, we expect to understand the sequence, the optimum sequence of visits, and also the schedule of each visit during the day. Next. So in any mathematical model, we expect to see an objective function, which is the achieving the goal of the model. And then there will be a set of constraints, because in the real world, there are some requirements to be met and also some restrictions and limitations that we need to consider. So we wrote them as the constraints of our models. So the first line is our objective function, which is minimization of maximum lateness of the visits during a day. Basically, there's a due date for every single visit, and we want to make sure that we visit the locations on time. The first constraint is ensuring to calculate this objective function, knowing that there is a completion time for each visit and there is a due date for each of them. Constraint 3, 4, 5, 6, and 7, and also 8 are used in order to guarantee that all visits of all locations will be fulfilled by one of the drones that we have in the network. Constraint 9 and 10 are utilized to calculate the completion time of each visit. So here in constraint number 10, we do have multiplication of two binary decision variables, which makes the model nonlinear. Whenever we have nonlinear model, it means that the optimal solution might not be guaranteed, and also commercial solvers that we have in the market might not be able to actually provide any solution to the model. So that's important. We have to come up with a linearization approach for this constraint, and we did. So it means that constraint number 10 going to be replaced by a sets of new linearization constraints. The constraint 11, 12, 13, and 14, and 15 are dedicated to ensure that if a consumed change, if the consumed charge by the drones exceed the available charge, then we have to send drones to the charging station. Here again, we do have some multiplication of integer variables and binary variables. We have to linearize that by replacing these two constraints with 6 other constraints. Constraints 16 to 18 are there to guarantee that the time difference between two consecutive visits to a location does not exceed the available minimum and maximum intervisit time. Again, here we do have nonlinear constraints. We have to replace them with linear counterparts. So basically, at the end, we're going to need to run this model and find out the optimal solution for routing, scheduling of the drones in a highway network. We are using Python linear programming API with General Solver CVC, and we are running the model in actually the HPC resource that has been provided to us. So in the literature, it is proven that scheduling multiple machines with the objective function of minimization of maximum lateness is an NP-hard problem, meaning that the amount of time required to solve the problem increases exponentially as the size of the problem increases. Right now, we are actually running small size problems, which takes less than 2 minutes to give us the optimum solution. But we expect as we increase the size of the problem, the runtime going to increase exponentially. And that's why we are using HPC resources to run our model and find a solution. For the sake of this presentation, I am providing a small example. In this example, we assume that we have 3 locations to be visited on the highway by drones. Each location has different number of visits. We have 2 drones in this small example. Each visit has a due date. There is a travel time between the depot or charging station to each of these locations and between locations. Each drone gonna stay in the visited area for a while to monitor the situation and exchange information to the associated parties, specifically if any incident happens. And also there's some charging requirements, and each drone gonna have to get back to the depot charging station if needed. The output of our model gonna be the sequence of operations for each drone. For example, here drone number 1 gonna visit location 1, then location 2, and get back to location one more time. It's gonna go to depot because it needs to be recharged, And then after charging, it's going to get back to location number 2 for monitoring the situation. In the meanwhile, drone number 2 visiting location 3 and then location 1, going to go back to depot for recharging and gets back to location 2 and 3 for the final monitorings. The model also provides the schedule of each of these visits, specifically considering all the requirements that we have in the real world, as well as the all the due dates and the maximum intervisit times. So just as a brief conclusion, we have introduced a new mathematical model for routing and scheduling of multiple drones in order to monitor highways and also make sure that we can provide fast responses in terms of emergencies. This is an effective, flexible, and cost-efficient solution compared to the traditional ones. As I mentioned, this is an ongoing research, so we are still working on finding case studies, specifically in Inland Empire, hopefully to be able to solve large scale of the problem and also considering the real world setting. Finally, we would like to thank the High Performance Computing Program team at CSUSB, specifically Dr. Kim and also Dr. Wu for their help with setting up the environment for our computations. Thank you so much, and we'll be happy to take your questions.
Thank you, Dr. Mohabati and Dr. Alavi. This team is pretty new to high performance computing, and we're very excited to have them using the high performance computing resources. So those are all of our presenters today, and I think our audience and the fellow presenters can see what a wide range of kinds of research, even in this small sample, from human health and archaeology to material science and logistics. And we would like to invite any of the audience members to contact Dr. Kim or me. Here's Dr. Kim's address again. I'll type it in here. Yep, and we would love to assist with any projects that you think may be able to use the high performance computing resources. Also now, if the presenters have any questions for one another, I invite them to ask them now. And if our audience members have any questions for presenters or for Dr. Kim or Dr. Vu, I invite you to submit them there. Okay, we have a question from an audience member. How many groups are interested in Unreal Engine? I saw Dr. Liska and Professor Kramer use Unreal Engine. Do any of our other presenters use Unreal Engine or are interested in it? Professor Kramer, yeah, Young-Soo, please.
The group that might be interested in with Unreal Engine might be the X-Real Lab. Those people might be interested, but I'm not 100% sure.
Thank you, Young-Soo. Professor Kramer or Dr. Liska, did you want to say anything about it?
Yeah, we've worked with X-Real on a number of ideas about what we can do with this project, and we ourselves have kind of played around with Unreal Engine from the beginning of the pre-release of 5.0. And it's amazing. I mean, it's designed to handle with the kind of situation that we're dealing with of having very high data products that come out of this. Unfortunately, with virtual reality, usually the data products need to be really low res to be able to work well, but this is part of the industry changing its tactic, trying to allow people to do models of anything in high res. And for archaeology, that's hugely significant because details are, that's where we live. So Unreal Engine is a great resource for that, and it's going to change the industry of 3D modeling that way.
Thank you, Professor Kramer. Do we have any further questions from our audience members, either in chat or through Q&A? or any questions from our presenters to each other or to anyone else present today?
I have a question for Ben, if it is okay.
Yeah, of course. Thank you.
So we are in the same department. So Ben, you talked about it's first of all very interesting research that you're doing with all the students. So I was wondering what kind of methods you are thinking about for implementation of interpretable machine learning.
Oh, sure. Good question. So we're thinking of using SHAP values first. So that's kind of been out in the literature for a little bit. There's also these other types of newer models where I don't know. I think I want to try it out because there's not that much documentation on it. Like there's one called like neuro additive models, which are supposed to be like a deep learning approach, but it will also provide some insight into like how the features are predicting your outcome. So that's something I want to look at too. But we definitely want to start with something where has a high chance of actually predicting the outcome. So that's why we're going to go with SHAP values.
That's very interesting. Actually, I have a publication in SHAP value for ranking and recommendation and interpretable ranking and recommendation. So yeah, it's very interesting and it has a very promising result. So I'm sure that you find it interesting as well.
Oh, for sure. Yeah, maybe I can contact you later. You could share that with me.
Of course, be happy. Thank you.
Thank you.
Thank you both. And I'm putting the website link to our HPC website, in the chat for our audience members. Are there any other questions from our presenters to one another or about anything else?
I had a question for Dr. Mahabati and Dr. Alavi about the model that you've constructed. I didn't see, maybe I missed it, the factor of maintenance and spot checking the machines as part of the calculation for the best model. In my use of drones, I found that needs to be an essential element to the process of running and working with them, because something can go wrong and the catastrophic failure will just turn off the whole use of it. Did I miss that? Was that part of it, or is that under like charging?
That's a great question. Yes, definitely, it's very important to check the drones continuously for all the maintenance and everything. We assume that drones are visiting depots often during the day, so for recharge and also definitely for maintenance check. So it can be considered part of visiting the depot. Thank you for the question. We will definitely think more about that.
Thank you both. Any other questions? Hearing none, I will thank our presenters for their fantastic presentations and for staying on time and for the unbelievable work you're doing with the high performance computing resources. Thank you all so much. And we thank our audience for tuning in. And again, please contact us if you have any projects you think might benefit from these resources. So thank you, everyone, and we'll see you soon.